Let's look at number 2 in the AP FRQ review. This is derivative graphs topic. The figure shows the graph of our piecewise linear function from -4 to 12. We have these linear graphs or linear piecewise functions, and our g of x is the integral from 2 to x of f of t dt. So part A, does our g function have a relative minimum, relative max, or neither at x equals 10? Now this notation tells us that the f is really sitting at the derivative of g level, right? Because it takes an integral of f of t to move it up to the same level as g of x. So let's just think of f as the derivative graph of g. If we're looking at the derivative graph, I like to label above being positive slope, below being negative slope. Anything on the x-axis is where slope 0, and wherever slope is 0 is going to be where our critical point is. And if we can create a slope sine line, we can pick out that there is a relative where we have change in signs at -2 and at 6. So we can say our graph is negative slope up until -2, and then from -2 to 6 is going to remain positive slope, or with no relative max, relative min, except at -2 and at 6. Negative slope from 6 all the way to 12. And is there a relative minimum, relative max at x equals 10? So at x equals 10, what happens is that we have a negative slope, and then we have a slope 0, but then it continues being a negative slope. There's no change in sign, so if there's no change in sign, we can say that's not it's a critical point, but it's not a relative max nor relative min. It is going to be neither. Okay, so neither relative max, relative min, since g prime does not change signs at x equals 10. For part B, does the graph have a point of inflection at x equals 4? So at x equals 4, we're looking at the derivative graph, so any peaks and valleys will be points of inflection. So we have all these peaks and valleys. These are all going to be points of inflection. But the problem is asking specifically at x equals 4, and there is a point of inflection at x equals 4 because our g prime changes from increase to decrease. For part C, find the absolute minimum value and the absolute max on the closed interval from -4 to 12. Justify your answers. So this is applying extreme value theorem. So extreme value theorem says find the critical points, find the endpoints, and test them against the original function and see which one produces the largest and smallest values. Okay? And largest value will be the absolute max value, lowest will be the absolute min. So we need to find our critical points. Our critical points will be relative max and relative mins. So we're only going to be targeting -2 because there's a change in sign here, and 6 where there's another change in sign. Neither 2 nor 10 has change in sign, so critical points, but neither a relative max, relative min, and we don't have to go through and test the relative max and relative mins. Just the relative max, relative mins. Sorry, 6, -2, -4, and 12. So they all go back into the original formula that represents g of x. So to find g of -4 first, I'm going to plug -4 into my formula. If I want to read the graph from 2 to -4, I like to read from left to right. So we're going to flip the bounds, make it go from -4 to 2. And from -4 to 2, we total those regions up. These are all triangles, so 1/2 base times height. I filled out all these area values, and anything below the x-axis I indicate as negative. Anything above I represent as positive. So if we want to go from -4 to -2, so -4 to -4 to 2, we'll have -4 plus 4 plus 4, and that's going to total region of 4. Okay, so it's going to give us a region of 4. However, there we flip the bound, so there's a negative sign in front, so that negative is going to force it to be a -4. To find g of negative 2, replace the upper bound with negative 2. Again, I'm having to read the graph up backwards. So I flip the bounds, read the graph from negative 2 to 2, keep a negative outside. From negative 2 to 2, we see our region is going to total to be 8. So we fill our integral, replace it with 8. But keep in mind that we flipped it, so there's that negative sign we got to keep track of. So negative times 8 is going to be negative 8. Okay, next critical point, g of 6. So to integral, find definite integral from 2 to 6. There's no need to flip the bounds. It's already in order from smaller to larger. So from 2 to 6, we total those regions to be 8. And then finally, g of 12, we want to span from 2 all the way to 12. So this 8 and this negative 8 will cancel each other out. We're just left with negative 4. And now we can compare the values. Comparing all these locations of our critical points and endpoints, we see the highest y value is 8, so absolute max value is 8 at x equals 6, and the lowest y value that we see is negative 8, and that's our absolute min value. For part D, find all intervals in which our g of x function is less than or equal to 0. So if we were to graph our original g of x function, when is the graph going to be below 0? And one thing that we can do is we can follow the path of the graph that we see in front of us. Okay? And we can also plot our order pairs. So a couple of order pairs that we know. We know order pair negative 4, negative 4. We know order pair negative 2, negative 8. We know order pair 6, 8, and we have the order pair 12, negative 4. Okay. So plotting all those points, okay. So here's negative 4, negative 4. Here's negative 2, negative 8. We also have, I also plotted 2, 0, because at x equals 2, we're getting 0, because the integral from 2 to 2 is just going to be, if the bounds are the same, it's just going to wipe out to be 0. So it's a point that I can use to help me kind of separate the regions here. We have an order pair of 6, 8, and we have an order pair of 12, negative 4. Now at 10, we're also getting 0, because the integral from 2 to 10 is going to be 8 minus 8, which is 0. So we know that at 10 is 0. And if we can have that information there, then connecting the dots, we can see that, all right, we have the region from negative 4 to positive 2 is where our g graph is going to be less than 0 or below the x-axis. And then it's going to have to be above the x-axis until it comes back to the x-intercept at x equals 10. And then from 10 to 12, it's going to be again below the x-axis. So our graph is going to be less than or equal to 0 from negative 4 to 2, and also from 10 to 12.